Hi guys, then we'll just give it a minute for see if we have other people showing up. How you guys doing today? Okay, so I think I'll just go ahead and get started. So I'm gonna go back to chapter 2.5, which is what we were talking about before, and kind of work through some of the stuff on chapter 2.5. I want to finish up the discussion about 2.5, and then I want to do some of the classwork problems for 2.5. If we have time, then we can kind of maybe start in on 2.6 as well. But let's finish talking about chapter 2.5. So if you remember, with 2.5, we have an isometry we were talking about. An isometry, it's a kind of a transformation. It's a way of describing a type of a transformation. So it's a transformation that preserves distance, right? So if I take an object and I move it over and up, I haven't actually changed the basic shape of that object, but it still has, lengths of the same length, angles of the same angle, okay? So things like rotations, right, or reflections will be isometries because they are preserving distance, okay? When we talk about linear isometries, we're talking about rotation, like some kind of a map, okay? And we've got different possibilities in our, hang on a second. We have different possibilities for checking out if something is a linear isometry, right? We have to check to see if each column on our matrix is going to have a magnitude equal to 1. And we also have to make sure that each column is perpendicular to every other column within our matrix. So there's also something in our concept of isometries. Oops, give me a sec. In our concept of isometries, and there's something called handedness. Here, hang on a sec. There's something that's called handedness. Okay, so when we talk about handedness, what that means is, right, you can think about if I have an object, like I have my hand, and if I were to rotate that object by 30 degrees, say, for example, my hand doesn't change position. It's still a right hand, right? I'm just rotating it or moving it around. However, if I take my hand, if I take my hand and I reflect it, I've changed the handedness. So now I've gone from a right hand to a left hand. It's changed it, okay? So we talk about handedness as a type of transformation that we're doing, the way that we can see. So this is, how can I describe handedness? Does the object look the same as when you first started? Right, like basically you haven't actually changed how the object is. Like I've taken it and I've moved it. So for example, if I have, say, a triangle that looks like this, right, and I've got A, B, and C, and I were to rotate it, I'm going to rotate that. So basically what I'm getting is I'm going to get, if I can draw this, like, I'm not trying this very well. This is A, B, and C. So I haven't actually, it's still the same object, it's just kind of rotated, right? Does it look the same as when you first started? Or has it, we can think of it as being like flipped. Like you've gone from a right hand to a left hand, right? Like you can imagine if I have, say, a triangle, A, B, and C, right? And I were to do a reflection, right? So if I were to do a reflection across this axis here, and this is my, I'll draw this in green, and this is my new triangle here. This is A, this is C. It looks different. It's changed its handedness, okay? So the way that we can tell if something is going to have a handedness, whether it's going to preserve the orientation, right? So this is, we can think of it as Write this in a different color. Preserves orientation, or it changes the orientation. Okay, so what we can do is when we think about our isometries, when we think about our determinant of our matrix, okay, so a determinant of a matrix is going to tell us whether or not our handedness is preserved or it isn't. Okay, so basically what happens is if I have, let's see if I've got a matrix M, I go A, let's go minus B, B, and A, and I go to find the determinant of M, for example, right? I'm going to multiply here. I'm going to get A squared minus B. This is going to be times B times a minus B. This is going to become A squared plus B squared. So my answer is going to be positive, right? So if my answer is positive, my determinant is positive, this is going to preserve handedness. Okay. If, say, for example, I've got a matrix that says A minus A, B, B, right? And I were to take the determinant of M, I'm going to get A times a minus A minus B times B. So what's going to happen is I'm going to get minus A squared minus B squared, which is going to be a negative number. Okay, if my determinant is negative, then it's going to change our handedness. Okay. Okay, so preserving our handedness happens in things like rotations. Okay, it doesn't change the orientation. Things where our handedness gets changed happens in reflections. Okay, so reflections are going to change our handedness. Okay, so it's an important concept that we need to think about. So let's take a look. If I look at my examples, example 11 and example 12. Okay. Second. I'm gonna bring these. Example 11 and example 12. So let's think. Oops, I think my daughter stole my calculator. Can you guys give me just a second? My daughter walked off with my calculator. I think I'll find it. Give me a sec. Sorry about that. She really likes my calculator because it's got all these different functions on it, and she likes to use it for her classes. Okay, so handedness of this transformation. So let's think about it. So I'm going to multiply. I'm going to take the determinant of our matrix, this M, determinant of M. So I'm going to multiply here. So this is going to be 0.8192 times 0.8192 minus, I'm going to multiply here, 0.5736 times a minus 0.5736. You can see where this is going, right? So this is going to be 0.8192 plus 0.573, okay, 6. Right, so this is minus times minus makes it plus. And so, whoops. So what I get is this is equal to positive 1. Okay, so what happens is this, right, it's a positive number, so it's going to preserve handedness. Okay, and it's also true, right? If I remember, I think we did these before where we looked at whether or not this was going to be right. We said that this was going to be an isometry. Okay, so we did this one here. So this one was actually an isometric, was an isometry, right, in terms of its translation. Now, because we already showed that it was an isometry, the fact that it's equal to 1 also tells us that it's going to be a linear isometry. So linear isometries will always have a determinant equal to 1. It's not true that not all that matrices that have an isometry equal to 1 will be linear, but it's true that all linear isometries will have a determinant equal to 1. Okay, this preserves handedness, and this actually is a rotation. Okay, we actually did this one before too. So this is a rotation by actually not 30, 35 degrees. Okay. So let's do this one. Now, example 12. Okay. So what's the handedness of this transformation and what does it tell us? So I'm going to do this is going to be 0.9537 times 537 minus 0.3007 times. Oops, so this is going to be the same thing. Did I goof this one up? This one is supposed to be, yeah, I think this is a, I made a mistake. This is should be positive and that should be negative. So that's going to be negative, and then this is going to be 007 there. Okay, so I made a typo. So this is positive and this one's negative. So I'm going to multiply these together, right? So I'm going to get, this is going to be negative 0.9537 minus 0.9095 minus 0.0904. Okay, when I add these together, I get this is equal to minus 0.99996. So this is like basically equal to -1. Okay, there's like some rounding because I'm like I had to round things up here. So this is negative, which means that it changes our handedness. So it changes it from this way, from a right hand to a left hand. Okay, so this changes handedness, and this is actually a reflection. And it's a reflection across the line. Across the line that of a line that makes a 35-degree angle with the x-axis. Okay, so that's how we're thinking about our handedness. Okay, right. So let's just talk for, I just want to make a brief point here about the handedness, just to make sure that we're on the same page about it. So I can use the determinants to help me tell like what's happening. Okay, so let's see, how can I describe it? To check to see if something is a linear isometry, you have to check if the column vectors are unit vectors. So they have a magnitude equal to 1. And you have to check that the columns are what we call mutually perpendicular. Okay, if both of those are true, then we're dealing with a linear isometry. Okay, and the determinant, which is what we just calculated, will be equal to a positive or -1. Okay, but it's not true that if I check the determinant and I find out it's equal to positive or -1, it's a linear isometry. I have to do this check to see if it's linear isometry. But let's write that down. But if we have a transformation matrix and the determinant is equal to positive or -1, that does not mean it is a linear isometry. We must check the columns. Column relationship. Okay, so if I have a linear isometry and I take the determinant, it'll be a positive or negative one, okay, because I've already checked that it's a linear isometry. The positive or negative tells me if it preserves handedness or if it changed the handedness, if it changed the orientation, okay, but the determinant will be equal to 1. I could have a matrix that has a determinant equal to positive or negative 1, but it doesn't represent an isometry, okay, or a linear isometry. So keep that in mind. They're not mutually exclusive like that, okay? So this is chapter 2.5. So what I'd like to do is I want to work through some problems from our classwork, and then, probably in a little bit, I'll take a step back, and then we can talk about chapter 2.6, okay? So you guys will have this here. Okay. Let me do this. Put that to the side. And I'm pulling out my classwork. It says classwork for 2.5 and 2.6. But I'm going to work through some of these here. And then we'll talk about chapter 2.6 for a little bit. Okay. Okay. So I'm just going to work through these problems for a little bit. And then we'll talk about 2.6. Okay. So give me, if you guys want to pull this out too, you can work on it at the same time. And then in, about maybe 10 minutes or so, we'll come back together and then go on to 2.6. Mhm. I'm going to come back to this one because this is a chapter 2.6 question. This is technically a 2.6 question also. This is a review, so we're going to work through this one too. This is a review, so this problem is a review, so I'll do part B also. I ran out of space on this one here. Thanks. Let's see. Another piece of paper. Last question. Right, so line segment. So I found the new translated vector, the new translated points. I had to come up with a line segment from here to here, right? Because we used to go from 0, 0 to 1, 0. Now these are my reflected points. So now I have my displacement vector from here to here is going to be terminal minus initial. So I subtracted, right, my terminal minus initial to get this as my displacement vector. So my initial point plus the parameter times the vector, and I have to restrict my t value. Okay, so that was 3b. So that was all, some of that was a review, and some of that question number 1 was new. You guys have questions on what we did on the classwork? So I'm going to take a step back and I'm going to look at chapter 2.6 now. I'll come back to this classwork page here. I'll scan in our 2.5 lecture examples later. Okay, put those up. Okay, all right, so let's talk about chapter 2.6. All right, so I've got my lecture examples for chapter 2.6. I'm going to pull those out in a little bit. And we're going to start working our way through. Put that out. Okay. All right, you ready? So chapter 2.6, we've kind of been doing, this is called determinant of a matrix. We've been kind of doing this already. We talked about it actually at the beginning when we talked about the cross product, right? So the cross product is, it's kind of a similar process to how we calculated a determinant, okay? So let's think about how, what we're gonna do for a determinant, because the determinant actually tells us a lot about the matrix itself. One of the biggest things that it tells us, whether or not a given matrix is invertible, right? Does that matrix have an inverse? And that's important for transformations, because if a matrix has an inverse, then I can do the transformation and then I can go back to where I was originally. We can undo the transformation that we did before. Okay, so determinant actually tells us a lot. So what am I trying to say? If the determinant is equal to 0, then there's no inverse. Okay, so if the determinant is equal to 0, then no inverse is possible. Okay, so it's also going to tell us interesting things about, this is one possibility. It tells us about whether or not it's invertible. It also tells us, okay, it'll tell us about whether, so let's see, determinant about the handedness of our transformation, right? So if it's a positive, it preserves the handedness. And preserving the handedness is going to become important, because think about it, if you are changing the handedness, that means now when you're recreating your animation, your shape, wherever it is, you have to think about how the shading and how the design is going to be different, right? It's not just so that I can reflect it and put it into its spot, but I have to think about like how I'm going to rebuild that, because to rebuild the rest of it, you know, how I'm going to shade it and how I'm going to make it look, okay, because I need to take into account that the handedness has shifted. Okay, so it's positive, it preserves the handedness. If it's negative, then it changes, it flips the handedness. It changes the orientation of the object. Okay. The determinant will also tell us what is the area, if we're in 2 dimensions, of like, you know, of a parallelogram or of a square or of a shape, or the volume, we're in R3. Okay, so we're actually going to get to these things here. It'll tell us about that stuff. Okay, so let's talk about how do we actually do it. We've been kind of dancing around it for a while, so let's actually, you know, really do it for reals. Okay, so let's say I have a 2 by 2 matrix. Okay, and we'll call it M. When I want to take the determinant of M, right, I can say determinant of M, right, and let's say M is equal to, I'll call it A, B, C, D, like this. I can say, let's take the determinant of M, and it's going to look like, remember, we used this symbol when we were calculating the cross product of things, right? Because in doing the cross product, we were actually taking the determinant, okay? So I'm going to do the same thing like I do for my cross product. I'm going to multiply on the crisscross here, and then multiply on the diagonal. So that's going to be A times D minus C times B, and that's going to give me my determinant. Okay. Right, I'm running out of space here. Okay, so this is a 2 by 2 matrix. I'll do a 3 by 3 matrix, just as an example. And I'll call this A, B, C, E, F, G, H, I. We've been doing this with our cross product, right? Now, when I go to take a 3 by 3 determinant, there are different shortcuts that I can do, okay? And I can also do things based on different rows or different types of expansions, but I'm going to keep it consistent with what we've done with our cross product. So I'm just going to keep it like how we've done with our cross product. So I'm going to say this is A times the determinant of like what's left over, right? So this is going to be first row, first column. I take my E, F, H, and I. So this is just like our cross product, minus B times first row, second column, E, G, F, and I, plus C times first row, third column, E, E, G, and H. And this is going to give me a number, scalar. It's going to be positive or negative, right? Depending on, you know, what our values are turning out to be. It's not going to be a vector. It's going to be a number. Okay, the determinant is a number. It's not a vector. It's just a scalar number that we're getting out of things. Okay, so this will also extend, right, into higher dimensions, 4 by 4, 5 by 5. I need to have a square matrix in order to do a determinant. Okay, but we're only going to cover 2 by 2 and 3 by 3 because the higher dimensions are out of the scope of this class. But just so you know, you could take the determinant of any higher ordered matrix. You just start nesting. So for example, it was a 4 by 4. I did the first row expansion like we've been talking about here. Then I would get the first position times the matrix that was left over, and then I'd have to do a 3 by 3 determinant on the inside. So I'd be nesting all the way down. Okay, it's a pretty computationally expensive process the higher up you go in your matrices. That's why we tend to look for rows or columns that have a lot of zeros in it, because it makes it easier in terms of doing all of our calculations. Okay, so determinant. Let's do some examples so that we can see what this looks like. All right, so Example 1, I'm on my lecture examples page. So find the determinant of this matrix. Okay, so remember, we're gonna, just like we did with our cross product, I'm gonna multiply across on the diagonal. So it's gonna be 2 times the minus 3 minus 1 times 1. Okay, and this is gonna be 2 times minus 3 is minus 6. Minus 1 times minus a minus becomes positive 1, which is minus 5. Okay, so if this were a transformation, right, I would say it's gonna change our handedness, right? It's gonna flip the handedness. Okay, let's do this one. Okay, so I'm gonna do this first row expansion. Like I said, outside of this class, when you take a determinant, you can do any kind of row or column as a determinant. But for us, we're just gonna focus on the first row to keep it consistent with our cross product. Okay, so this determinant is gonna look like 2 times 3406 minus 1 times minus 2 minus 1, 0, 6, 6 plus 1 times, I'm putting the ones in so you can see that I'm actually multiplying it through, minus 2, 3, minus 1, 4. Okay, so this is going to become 2 times, this is going to be 3 times 6 minus 4 times 0 minus 2 times 6 minus a minus 1 times 0. I'm putting in the times 0 so that you can see that those are happening, but you don't need to put those in next time. Unless it's a 0 here, and then you want to say 0 minus something, kind of keep yourself in memory that you actually have to multiply by a negative number. So this is 1 times, so I've got minus 2 times 4 minus a minus 1 times 3. Okay, so let's do this. So 3 times 6 is 18 minus 0. So 2 times 18 minus, this is minus 12 minus 0. This is a minus 8 minus a minus plus 3. Okay, so this is going to be a minus 5. All right, so 2 times 18 is 36 minus minus plus 12 minus 5. Okay, and this is going to be equal to 43. Okay. Let's see how we did that. Okay, so let's take a look. We're going to keep going. Let's talk about some properties of determinants. So some properties of determinants that we want to keep in mind. So the first property, if I take the determinant of our identity matrix, I'm going to get that's equal to 1. Very helpful to know. It'll save you having to do it. If I take the determinant of 2 matrices being multiplied together, A times B, that's equal to the determinant of A times the determinant of B. So if you happen to have calculated out the individual determinants, right, that may help you as opposed to doing this matrix multiplication and then the determinant there. Okay, sometimes this may be cheaper than this, or it may be cheaper to computationally to multiply the 2 matrices and do the determinant. We said this before, right? If the determinant of our matrix is equal to 0, then there's no inverse for that matrix A. Okay. Remember how I said you can do any kind of row or column expansion for the determinant, right? We just happen to choose the first row expansion on it. It makes sense that now if I do the determinant of the transpose of the matrix, it's going to be the same thing as though I were to be doing the determinant of the regular matrix. Okay, because when I do the determinant, I can do it on any row or column. We just focus on the first row to keep it simple. Okay, so if I have a linear isometry, I have a matrix that represents a linear isometry. I've already checked the column vectors, that they're unit vectors and that they're mutually perpendicular, right? The determinant is always going to be positive or negative 1. We said this before, this is about the handedness, right? So if our determinant is positive, then our transformation that's represented by our matrix A will preserve the handedness. If the determinant is negative, then the transformation represented by A will not preserve our handedness. Okay? This is like rotation. This is like reflection, say, for example. You guys finish writing that, and then we'll look at some other examples. Okay, so let's take a look. So example 3. So I've got this matrix here, cosine, sine, minus sine, cosine. So I'm going to find the determinant of that. So I'm going to multiply cosine of theta, minus the sine of theta, sine of theta. So this becomes the cosine squared of theta minus plus the sine squared of theta. This here is the Pythagorean identity, which is equal to 1. Okay, so this actually we should be able to recognize this is going to be a rotation by angle theta. Okay, so this is a rotation matrix. Okay, we can see we already talked before about how it was a linear isometry. We can see that the rotation matrix is going to have a determinant of positive 1. Okay, let's do this one. Cosine of theta. Okay, cosine of theta times a minus cosine becomes minus cosine squared of theta minus sine squared of theta. Now what I'm going to do is I'm going to factor out a minus 1 to get cosine squared of theta plus sine squared of theta. Okay. So now, right, we already just said this was our Pythagorean identity that was equal to 1. So minus 1 times positive 1 is equal to minus 1. Okay. So this one does not preserve handedness. This is actually our reflection by theta divided by 2. Remember how when we did our reflection matrix, it was cosine of 2 theta, sine of 2 theta. Well, now if I say this is theta divided by 2, that's the angle that I'm working with, and I can just call this cosine of theta. So that's how we think about that. Okay, so handedness is preserved, handedness is not preserved. Okay, I want to call your attention to, remember how I said you have to check linear isometry will always have a determinant of positive or negative 1, but just because the determinant is positive or negative 1 doesn't mean that it's an isometry. So let's do the determinant. So part A, we're going to take that determinant of 1, 1, 1, 2. It's going to equal to 1 times 2 minus 1 times 1, which is equal to 2 minus 1, which is equal to positive 1. Oh, looks promising. Is that a linear isometry? Let's check. I'm going to check the column vectors. The column vectors must be, they have a magnitude equal to 1. So let's check that one first. So I'm going to take my first column, column 1, 1 squared plus 1 squared square rooted, which is a radical 2. Whoops, my first column bombed out, right? My first column bombed out. It's not a unit vector, right? It doesn't have a magnitude equal to 1. Therefore, it's not a linear isometry, even though the determinant is 1, right? So checking the determinant will not tell you if something is a linear isometry. You must do the check on the columns, okay? If the column vectors are unit vectors, they have a magnitude equal to 1. And if the columns are mutually perpendicular, so they're perpendicular to each other, okay? If that's not true, but they have a determinant equal to 1, it just happens that they have a determinant equal to 1. What that means is I can find an inverse to this matrix, okay? And it's positive, oops, sorry, it's positive, so I know that I can, it's going to preserve the handedness on it, okay? All right, so let's check, is this transformation map invertible, okay? So let's see, I need to figure out what my determinant is. So let's check the determinant, 1, 0, 0, 0, that's a 0. Okay, which is going to be 1 times 0 minus 0 times 0, which is equal to 0. Okay, it is not invertible. Remember we talked about inverses. The inverse of the matrix is going to be 1 over the determinant times, remember if I have A, B, C, D, right? I'm going to switch A and B and I'm going to negate C. Oops, sorry, switch A and D, that's a D. And I'm going to negate C and B, okay? That's a D. There. Right, so if my determinant's equal to 0, I'm going to get a 1 divided by 0. That's going to cause a big problem, okay? So if my determinant's equal to 0, I can't get an inverse, okay? So let's try this one. Is this map invertible? Why or why not? So let's try our determinant. Okay, so I'm going to go 4 times 5, 0, 0, 1. I think it's a projection, looks like a projection map. I'm guessing probably not, but let's prove it to ourselves. So 4 times what's left over minus 0 times plus minus 2 times. Okay, so let's work it through. So 4 times, this is going to be 5 minus 0. Minus is 0, 0 times this, plus this is a minus 2 times, this is going to be, did I do this right? 4, 5, 0, 0, 1. Okay, so this is going to be 0 minus 10. Okay, so this is going to be 4 times 5 is 20, minus 0. This is going to be positive 10. So minus 2 times positive 10 becomes a minus 20. 20 minus 20 is equal to 0. So my determinant is equal to 0. Therefore, no inverse. Which we said before. Remember, when we were talking about projection maps, we said projection maps don't have inverses, right? Because it's not a one-to-one relationship between my input and my output. So I can't go back, right? It's not like when I rotate, I can rotate back, okay? So the projection maps don't have an inverse, and now I know why. Also because there's no, the determinant's equal to 0, okay? Okay, so let's do this example here. All right, so we've got this transformation matrix B. B equals minus 2, 2, 1, 3. We want to sketch the parallelogram, which results when the unit square is transformed by B. So let's first talk about the unit square. Okay, so the unit square. Unit square is each side 1 unit in length. And it's generally, its corner is at the origin. It looks like this typically. Okay, so my unit square goes like this. Here's my origin is 0, 0. Here, here. It's basically made up of my unit basis vectors. Okay, so that's my unit square. So each vertex is this. I've got 0, 0, 0, 1, right? I've gone up. I've got 1, 0. I've gone out. I have 1, 1. Okay. So now what I want to do is I want to transform matrix want to transform this unit square by this transformation matrix B. Okay, so I'm going to go like this. B times my unit square. Coordinates. Okay, so we'll do that. Oh, I'll do that in a different color. So I'll do that in green. Okay, so I'm going to go like this. -2, 1, 2, 3. Oops, I probably should have drawn there. Times, I'm going to go times 0, 0. So 0, 0, that's 0, 0, 0. So this one doesn't change. Okay, so I still have, I'm going to start drawing it out as I go. So that one is still centered at the origin. Right, I'm multiplying first row, first column. That's how I'm getting these numbers. So I've gone over 2 and I've gone up 3. So I've taken 0, 1 and I've moved it to here. Okay, now -2, 1, 2, 3. I'm going to transform 1, 0. So that's going to be -2. Okay, so I'm going to go -2, 1. Okay, -2, 2, 1, 3. And I'm going to apply that to 1, 1. I'm doing it to each of these vertices, right? All right, so now what I'm going to say is -2 plus a +2 is 0. 1 plus 3 is 4. So I'm going 1, 2, 3. Oops, and I need one more, 4. So here's my parallelogram. Okay. And these were all coordinates for that parallelogram. Okay. Now, sketch the parallelogram, which results when the unit square is transformed by B. That gives us this. Find the area of the parallelogram that results from this transformation. Okay, so my area now, I can just take the determinant of my parallelogram. So the determinant of B will give me the area of unit square transformed by B. Okay, so, and that's because I'm transforming the unit square. Okay, otherwise what I would need to do is calculate a vector here, calculate a distance vector there. Okay, and then I would be multiplying base times height. Okay, but right now we're just going to be using this. Okay, so now I'm going to go determinant of B. So I said that's going to be -2 times 3 minus a 1 times 2. So this is, and I have to take the absolute value of that because my area is going to be positive numbers. This is absolute value -6 minus 2, which is equal to +8. You know, area always has to be positive. So this is 8 units. Okay, the area of my unit square was 1 unit, right? It was 1 times 1, just 1 unit there. Okay, so now part C says, let's find the inverse of B. Okay, so B inverse says we need to find, which is 1 over the determinant. And then I have to swap A, B, C, D, right? So I have to swap D and A and -C and -B. Okay, so now I need to take, I took the absolute value to get that this is the determinant is equal to -8, but I need to make it the absolute value of the determinant to get my area. So my determinant was equal to 1 over -8, and I'm going to swap D and A. So this is going to be 3 and -2, and I need to negate this and negate that. And because I have a negative here and I've got so many negatives there, I'm just going to distribute the negative. This is going to be 1/8. It's going to be -3, +2, +1, +2. And I can even put in this 1/8 into there. So I can make this -3/8. This is going to be 1/8 times 2, so that's 1/4, 1/8, 1/4. And this is my inverse. Okay. And I think what I'm going to do is I will come back to this one, come back to part D. I'm going to come back to that next time because that's going to be a whole multiplication thing. show that this inverse will bring us back. And I want to talk about how we actually do that. Okay, so I'm going to talk about this on Monday. And then we'll work through some more of our classwork problems for chapter 2.6. Okay, guys? Don't forget, Monday, we also have a quiz. Okay, so what I'll do on Monday is I'll end class a little bit early, right? Because like normally if we were in class, I would teach for half the period and then you guys would take the quiz in the second half of the period. But what I'll do is I'll teach for half the period, finish up this stuff here, okay? Answer any questions that you may have, and then we'll end early so that then you can take the quiz, okay? All right, you guys. So that's it for today. And hope you have a great weekend. Stay safe. I know Halloween's coming up this weekend, so stay safe this weekend. Okay. Bye.